Hello everyone, my name is Andy Wang and I'm a researcher in the Statistical Science Group at the Maths Department at the University of Bristol. And today I'm going to introduce you to my field of research, which is Monte Carlo methods. So in your studies so far, you may have come across integrals and how to calculate them. For example, you may have learned how to integrate a function like x squared. You can simply write down the antiderivative and compute its value by hand. But in science, the integrals we come across are considerably more complicated than this. They might look something like the following. This comes from a model in astronomy. And the number of dimensions here isn't equal to 1, but it's actually equal to n, which could be, say, 100. So what we have is a complicated 100-dimensional integral. We want to know its value because that's important for scientific understanding, but we simply cannot write down the numerical value by hand like we did before. So how would we compute it? Well, you'd have to use a numerical scheme on a computer to approximate it. So let's think for a moment what such a scheme might look like with a really simple example. Let's suppose we just wanted to approximate the area of the circle. Of course we know the exact area, it's pi. But we can think now for how we might develop a scheme to approximate its area. Because remember, you can think of integrals as calculating volumes in higher dimensions. And so what might you do to calculate this area approximately? Well, in your mind's eye, you might think you'd lay a grid, say, on top of the circle, and simply count, if you like, how many squares are inside it, because we know the area of a square. And so if we counted, say, how many squares have centers inside the circle, here we have 16, the green dots, we can simply count up the area of 16 squares and use that as an approximation for the area of the circle. And so in this case, we get 2.56. And now we realize this isn't a very good approximation of the area because well, the squares were too large. So if you wanted an approximation that was, say, twice as good, we could halve the length of the square. We could use a grid that's twice as fine, like this. And once again, we can look at how many squares have their centers inside the circle and count them up and add up those areas, and we get a much better approximation. And of course, if we're not satisfied by that, we can halve again and again. And each time we get an estimator that's twice as accurate as the previous one. But let's pause now for a minute and think about how much it costs to do this halving. Each time we got an estimator that was twice as good by halving the length of the square, but the number of squares wasn't doubled. It was actually multiplied by 4. Because remember, one square gets split into 4 squares, each of which has side length half of the original length. And that was in 2 dimensions. If we're in 3 dimensions, imagine splitting a cube into smaller cubes, each with half the side length. Well, one cube gets split into 8 cubes, which is 2 cubed. But our original integral was actually in 100 dimensions, and so if we were to split a 100-dimensional hypercube into smaller cubes, we'd need 2 to the power 100 times more cubes. And now 2 to the 100 is an astronomical figure. It is absolutely huge. And what is that saying? Well, that basically means that we cannot use these grid-based methods in high dimensions. They're far too expensive and slow to run on a computer. And so that's why Monte Carlo methods were developed. What would a Monte Carlo scheme look like to approximate the area of a circle? Well, Monte Carlo schemes are not interested in splitting up the space into squares or cubes and counting them up. Instead, Monte Carlo is going to use a random scheme to approximate the area and then some kind of averaging. In case you're curious about the name, Monte Carlo is an area in Monaco, and one of the founders of Monte Carlo methods, Stanislav Ulam, had an uncle who would often gamble at the casino in Monte Carlo. And so back to the circle, I've constructed a Monte Carlo scheme, and what that looks like is it throws points randomly into the square. I've constructed what's called a Markov chain, which moves around at random. I couldn't tell you where the next point will land. And if the point lands inside the circle, I've plotted it as green, and if outside, as red. And now we run this stochastic process for a long time. So we can fast forward to the end, when there are lots of points, and it looks something like this. And because of the way I've constructed the process, we can simply look at the proportion of points which landed inside the circle as a fraction of the total number of points thrown, and that will give us an approximation of the area, which in this case was about 3. And now this may not impress you very much. After all, our grid-based approach got more accurate estimates. But the benefit of Monte Carlo lies in the cost as the number of dimensions increases. Remember, we previously saw that the grid-based approach, the cost was exponential in the number of dimensions. It turns out that Monte Carlo schemes scale only polynomially, which is a cost that in practice we can afford. And furthermore, there's a theorem from probability theory called the central limit theorem that tells us that regardless of the number of dimensions, we can halve the error by using 4 times as many points. And that's true no matter how large the dimension is. And so today I've introduced you to the heart of Monte Carlo, which is to use a random scheme and then some kind of averaging to approximate quantities we're interested in. And Monte Carlo itself is a highly interdisciplinary field which draws tools from statistics and probability and also numerical analysis and computer science. And now is a particularly exciting time to be thinking about Monte Carlo because such methods have very wide application in all kinds of applied science such as computational physics, as well as modern algorithms in machine learning and Bayesian statistics more generally. So I hope you found this introduction to Monte Carlo methods interesting. Thank you for listening.